All right, so we're in the section where we are trying to figure out the volume of solids. So we did two yesterday. We looked at the volume of a solid where the cross-sectional areas were slices. So we had a base, and then we put like slices of bread or something here, and we made a solid. And then the second kind was we had a region that was filled in, and we took this region and we rotated it about an axis, which we did was the x-axis. And when we rotated it about the x-axis, we got a volume. So I want to do the same thing with this function right now. So for the first problem, the function that is graph, this is the graph of the function. F of x is the square root of e to the minus x squared between x equals 0 and x equals 2. So if I just go ahead and draw something like this, that just gives it an axis. Okay. All right. Okay, so here's my problem. And in this problem, my base is this region R. So this region is the base. Okay. And so here's my first problem. Okay. So the first problem is to find the volume of the solid if the region above is the base and the cross-sectional areas are perpendicular to the x-axis are squares. Okay, so that means that here there are squares that are sticking up out of this so at every x, there is a square that is sticking up perpendicular to the x-axis. Okay, so given this x right here, between 0 and 2, this is an x that is a square. Okay, doesn't look too much like me trying to make it look a little bit more like a square. There we go. Okay, it's a square. So basically, what does that actually mean? It means that if I were to draw this thing on the plane, on the XY plane, it means I actually have this function which looks like this. On the ground. So this is the function, and this is the region, and it's laying on the ground. And then standing up out of this region is our squares. So there are squares that are standing up. Okay, so you can see my areas that are standing up in the air right there. Okay, any questions about that? Okay, so they're standing up in the air, laying on top of this thing. So that means down here is another little square. Whoa, I don't want you looking like that. I want you to be green. And why are you doing that? Stop it. Okay, there you go. So there are squares standing up. All right. So what is the area of any of these squares? Well, let's figure this out. So the first thing we did was we drew it. So 1, we drew this thing. So 2, we need the limits of integration. Where do the squares start and where do the squares end? Can anybody give me that answer?
Is it 0 to 2?
0 to 2. Okay, so the squares start way down here when x is 0 and they keep going all the way down to x equals 2. Okay, so that's the limits of integration. 3, well, we identify that our cross-sectional areas are squares. So our cross sections are squares. So in 4, I need to find the area. So the area of a square is the length squared, whatever the length is. So the area of any square is the length squared. Okay. So now if the length is squared, let's look at our area. So here's our area that's standing up in the air. And these are our lengths, L and L. So they're the same. That's the length. Okay, how long is that length? Well, for any given x, this distance from here, from the bottom all the way up, well, that is simply whatever your x is, that's your y, or your y is equal to f of x. So that means that this length that we're looking at right here is simply y. So that means the length is simply the square root of x times e to the negative x squared. So that's the length, because it lays on, it's lying flat on the ground, and the squares are perpendicular to the x-axis. Okay, so now we have a formula. So we have the area, it's the length squared, but that's the square root of x times e to the negative x squared. So that is the square root of x squared times e to the negative x squared squared. So that is x e to the negative 2x squared. Okay, so now we have a formula. So that formula is a function of x. We call it a of x. So the last thing we need to do is the volume is the integral from a to b of whatever my area is, dx. Okay, so that's not too hard. Our volume is the integral from 0 to 2 of x e to the negative 2x squared dx. Now I need some brave soul to jump out there and tell me how to integrate this. Hello.
I can try it.
Okay.
do we need to find, well, take u and then
Yes,
to start off, so it would be negative 2x squared,
okay.
and then the derivative of that would be negative 4x, and then, oh yeah, dx.
Okay, all right, good.
And then after that, divide by negative 4x.
Okay. Do I want the X too, or just I want to leave the X where it is?
Oh wait, no, leave the x where it is because you want to
Yeah,
have,
you're right. I have X dx, so I want to leave
yeah.
the X where it is. Okay, awesome.
So now you can substitute, um, wait, was that right?
That's all that you've done so far is absolutely correct.
Oh, we have to, don't we need to replace, um, e, negative 2x squared with u?
Okay,
And then after that, replace dx with
X
negative,
dx.
oh
X,
yeah, x dx with negative 1/4 du.
and what about my limits of integration?
Um, they still need to be brought down, right?
Okay, but they need to change as well. We want everything to go from X to U.
Um,
So,
oh, we have to, um,
so if X equals 0, what is U? You plug X equals 0 into your equation for U. So what do you get?
0.
0. Good. And if X is equal to 2, what is U?
Mm, so wait,
Take X equals 2 and plop it in there.
oh shoot, I'm sorry. Um, it's gonna be negative 8.
Good. All right, so now we can move. So when X is 0, U is 0. And when X is 2, U is negative 8. Okay. So now we are ready to do this integral. So V is the negative integral, negative 1/4. We can pull that out. The integral from 0 to negative 8 of e to the u du.
I
Okay,
have a question.
yes,
Why would the negative 8 be on top if it's less than 0?
because it doesn't matter where it go, what the value is, it has to correspond. So here I have 0, X is 0, U is 0. It stays on the bottom. I
Okay.
have 2, X is equal to 2, U is negative 8. It stays on the top.
Okay.
Okay, that's very important. Okay, keep going.
And then we need to substitute everything back in.
Okay, no, we got to do the
Wait,
integral first.
oh, I'm sorry. Oh
So the
yeah.
integral of e to the u du is what?
Well, yeah, that.
That's the fundamental one. The integral of e to the u du is the only functions whose derivative and integral are equal to itself is the exponential.
So it's just, I'm confused.
What's that integral?
The EU.
Yeah, it's just gonna be e to the u.
It's just e to the u. So over here, I just get e to the u, but I have to evaluate it between 0 and -8. So I get -1/4 e to the -8 minus e to the 0, which is 1. Now I'm going to switch it and make it 1/4 e, sorry, 1 minus e to the -8. All right, Rodney, are
Yeah,
you okay now with that?
yeah, I'm understanding now.
Okay, so the problem was this integral that we started with was crazy. It was x e to the minus 2x squared dx. We did all that work and got that thing down to e to the u du. That was the purpose, to take the more difficult problem and break it down to something that's easier to work with. Okay. All right, so that's the answer. We're done. Oh, I already put a period there. So that's the volume of that paperweight. All right, I think it would be a cute paperweight. I'd like to see it. If it had that nice little base, I think that's a kind of cool function. Okay, so the second problem is to use the disk method. All right, so let me grab the second problem. Okay, so the second problem says, consider the region bounded by the curve f of x above, which is the same region we had. Okay. And then it's bounded by the lines y is equal to 0 and x is equal to 2. So I'm going to pick up that region and move it to this other part of the problem, because I decided to use the same region. Okay, so this is a different problem now. Now I'm going to take this region, and here's the solid. This is the solid of the region. Again, it's still a flat piece of paper or whatever you want to call it. And this time I'm going to rotate it around the x-axis. So here is okay. Same region between 0 and 2. So consider the region bounded by the curve f of x above by the lines y equals 0, that's the x-axis, and x equals 2, that's on the right-hand side. So I have that region. What is the volume of the solid generated by revolving the region about the x-axis? So when I revolve it about the x-axis, every point is going to revolve around the x-axis, and when it revolves, it's going to make a circle or a disc. Man, that was a hard coming to get that word out. Okay, so when I revolve it around the x-axis, I get something that looks like this. Okay, that's not too bad. I think I did the same thing. Too deep. Okay. There you have it. So I'm going to choose an X. Here's some X. And then here's the Y value, and that Y value gets revolved around the axis like this, and it creates a disk. That's not a bad disk at all. Okay, so this is the area that gets moved through 0, 2. So I see my disk. There's my disk. And my disk, I need the radius of it. So here's the radius. Okay. So the radius is that height. Well, we already figured that out for the last problem. We said that this height was simply y. All right, and we know that f of x equal to y is the square root of x times e to the negative x squared. Okay, so therefore the radius of this disk is equal to the square root of x e to the negative x squared. Now, when we use the disk method, we get the volume, the integral from a to b of pi times the radius squared. That's the whole radius dx. Okay, so for this, the radius of that disk, oh, okay, that looks like the integral from 0 to pi. Oh, no, from 0 to 2 of pi. And then I'm going to get the square root of x e to the negative x squared dx. Isn't it nice we computed this in the first problem? This is pi times the integral from 0 to 2. Uh-oh, go back. Let me stop. The integral from 0 to 2 of x e to the negative 2x squared dx. I computed that already. I don't have to do that again. This is pi over 4 times 1 minus e to the negative 8. Okay. So that is how you compute the volume by using disks. Okay, you start with something, you rotate it around. That means you filled in a region that's a disk or a circle, and then you're going to integrate or add up all the disks along the whole thing. And so as you can see, you kind of get an idea of what this thing looks like. I finally figured out what it looked like. I couldn't figure out, it's a bulb. It looks like a bulb. Okay, it could be a tulip bulb or any other bulb, but that's what it looks like. Okay, any questions about that? Any questions? Okay, I'll try to put together another Kahoot. I have some more integrals and stuff to give you guys a chance to do it. All right. Don't worry about who's first, who's second, and who's third. I'm looking at the number of points that you accumulate when you do. All right, guys. That's it for today. Thank you. Thank you.
Have a good day, Professor.
All right, you too.